This video is on testing the difference between means for large and independent samples. Now let's look at this definition for independent and dependent. Two samples are independent if the sample from one population is not related to the sample from the other population. They're dependent samples if each member of one sample corresponds to the member of the other sample. Quite often dependent samples are the same group of people with two different measurements. And dependent samples are also known as paired or matched samples. Let's take a look at these examples. Number one, sample 1, systolic blood pressures of 30 adult males. Sample 2, blood pressure of 30 females and 30 males. That would definitely be two independent groups. But the second one is, first sample is midterm exam scores of 14 chemistry students, and sample 2 is the final exam scores of the same 14 chemistry students. We would consider that to be dependent samples, especially since they're coming from the same group. Other examples you might see of dependent samples are, say you took a group of students that took like the SAT, and then they all took a prep course for the SAT, then took it again, and then tried to measure the results. That would be a dependent sample of the same group. Or a group, perhaps, that you measure their resting heart rate before exercise and measure it again after exercise. That would be a dependent group. But for example, if you took different groups and measured their heart rates, then those would be independent samples. All right. Here's an example over the right of time spent online. This would be two independent samples. So you say the average of males here is 85 minutes, standard deviation is 15. We had a sample size of 200. And then for the females, we're saying their average was 81 minutes, standard deviation was 17, and their sample size was 250. So kind of going back to what we talk about large here in this title, that's large generally means more than 30. I mean, really the larger the better. It's even better. 30 is not ideal, but that's kind of the cutoff point that we use for the Z distribution. Now, here are three basic setups for the hypothesis test. Now, so you can have, so instead of comparing these to a number, we'll compare them to each other. So here's mu1 equals mu2, so we're saying the two population groups are the same. Or do we reject that in favor of the alternative of them not being equal? Second one, mu1 less than or equal to mu2 versus an alternative of mu1 greater than mu2. And the last one is mu1 greater than or equal to mu2. And then mu1 less than mu2 would be its opposite. Now, to avoid any possible confusion regarding left-tailed and right-tailed tests, we'll treat the first group that we see in a problem as the first population, and the second group as population 2. So you can plan on that for any kind of test question. We'll go with that idea. Because this could be a little confusing for this right and left-tailed test if we didn't maintain some sort of order. So let's say we were trying to measure something that average female college students' GPA is greater than the men's male GPA. Well, there's two ways you could phrase that. You could say female greater than the male is the same thing as saying male less than the female. So there's kind of two ways you could write that, all depending on what order you word it. So if we read the problem and they gave us the female data first and the male data second, and we're saying the females are greater than the males, and we would use the right-tailed hypothesis here in the middle mu1 greater than mu2. I mean, you would still come to sort of, correct conclusion if it turned out that the data supported, the females being more, but how we word it, phrase it could be inconsistent, but it would still achieve the same results. In other words, if female was supposed to be greater than male, then you would also get male less than female if you worked it the other way. But let's, just so there's not two ways to set it up, we'll go with that logic every time. Okay, here's some basic criteria. Samples are randomly selected. Each samples are independent, don't depend on each other, and at least 30 or more, or if we know the standard deviation. All right. All right, so let's look at some of this now. All right, so we're going to have, obviously we have to have a z-score to be able to, z-test statistic to perform the z-test. So let's come down here and take a look at that. And this stuff right here in this box is going to be right down here also, so if you want to read that, that's fine. Now here's the test statistic, and why I have this crossed out as 0, because it is possible to perform a test statistic where even though I showed you those 3 rules up there a minute ago, you could do this as if you wanted to say group 1 was greater than group 2 by 10. In other words, mu1 minus mu2 would be greater than 10. We're not going to do that. We're just going to compare the groups against each other, whether one's equal, less than, greater than. We're not going to worry about a specific amount. So we're just going to say if it's less than, we don't care by how much. So, but theoretically, you could do that. You could do a test statistic. So I just cross that out, meaning that we're not going to have a mu1 minus mu2 equaling some number other than 0. So that just goes away. So the test statistic is your x1, your first sample mean, minus your second sample mean. And then it's divided by the standard deviation. And then over here to the right is how you get the standard deviation for x1 bar minus x2 bar. It's the standard deviation of group 1 squared, or the variance. So it's the variance of group 1 divided by n1 plus the variance of group 2 divided by the sample size for n2, and all that's tucked under the radical for the square root. Now, of course, it shows the population standard deviation, but just like before, anytime that most likely you're going to have the sample standard deviation, so being large enough, more than 30, we just use S1 and S2, and don't worry about whether or not we actually have sigma 1 and sigma 2. All right. Okay, let's see what this example says. From a certain hospital group in the U.S., we collect a sample of 80 doctors and find their mean IQ to be 118 and standard deviation 22. Sample of 70 nurses have a mean IQ of 128 and a standard deviation of 25. We claim that the mean IQ for the doctors is less than the nurses. And we're going to test this at a level of significance of 0.05. All right, so the first set of data in the problem relates to the doctors. So we're going to treat that as group 1. In other words, that mean will be x1 bar, that standard deviation will be S1, excuse me. So doctors less than nurses. So if doctors is group 1 and nurses is group 2, we will set up our hypothesis test then as follows. That's our claim that group 1 is less than group 2. So as I said before, whatever we see first in the problem is what we're going to treat as group 1. Whatever second is group 2. That makes it so you can almost write mu1, mu2. You can, then you can decide what symbol goes in there. So if the ha is less than, the null would be greater than or equal to. So all I did over here is write the two datas, values. Of course, the sample sizes don't have to equal each other. They just both need to be, by definition, large. So That's fine that one group was 80 and one was 70. That's all right. So that's just the written down information from up here. Now let's apply it and see what happens. So calculate the standard deviation. We follow that formula from back up here. And it's the square root of first standard deviation, 22 squared, divided by that n, which is 80, plus the second standard deviation, 25 squared, divided by that n, which is 70. And that's roughly about 3.8702, which you can see over here in the calculator box. So once we get that, we're good to go for the z. So the group 1 mean, x1 bar, is 118, minus the group 2 mean, 128, divided by that standard deviation we just calculated right here. And that will be negative 2.584. Now we're going to look at this two different ways. Of course, we have our p-value method that we've learned before. And we also have it using critical values. So for a left-tailed test, which this is left knee, left tail, less than, the p-value will be the area on the normal curve to the left of your test statistic. So if we look up negative 0.258 on the Z chart, we will have 0049, or I'll do it in the calculator using the normal CDF, second distribution, normal CDF. So we're coming from the left. So your calculator is going to show probably just parentheses. And you'll see in my other notes, just put in negative 100 is fine. This literally has a very, very, very small number, but I could change that to negative 100. It doesn't make any difference. But that's the representation for negative infinity. And the upper value is that z, negative 2.58. And then the mu 0 and the standard deviation 1, that's just indicated that this is our standard normal distribution z. Paste, so, all right, there we go. All right. So you see it's 0049. Like I said, don't worry about that negative 1e to the 99. You don't need that. So I'm not going to bring up the Z chart right now, but if you look that number up on the Z chart, by now you should be pretty efficient at looking up the Z chart. You would get that 0049. All right, so not much room there. Okay, so by definition, if your p-value is less than your alpha, your level of significance, you reject. So I do believe that 0049 is going to be less than 0.05. Therefore, that's reject. So we reject the null, and we do support the claim that the doctor's IQs, on average, are less than the nurse's. Okay, so that's really all there is to it. If we use that decision rule method, we would go back to that handout we've used for that, the decision rules. I think I will go ahead and bring this up. All right. I think common critical. So we have this for the left tail, right tail, two-tailed for the Z. So that's going to give me what? It's left-tailed test. Alpha's 0.05, so we have right here, negative 1.645. So we would reject if our test statistic Z is less than negative 1.645, which negative 2.584 is less than negative 1.645. Therefore, we reject. So you do come to the same conclusion with both methods. Now, you can do this in a calculator. It's a 2-sample Z test. Oh, there we go. Let's put this stat, test, number 3, 2 samples test. I find the way you enter the data to be a little bit strange here. I find this strange. You see it has standard deviation 1 and standard deviation 2, but it does not alternate the next group of info. It has X1 bar, N1, and then X2 bar, N2. Seems like it would alternate, 1, 2, 1, 2, 1, 2. But just as long as you're careful, you should be fine. So the first standard deviation is, go back up to the data, 22. Second one's 25. First mean is 118. I know one of these is 70 and one of them is 80. I can't remember. For the end. Okay, yeah, 128 was the other mean, but the group 1 is 80. And then group 2 will have an N of 70. 1, 2, 8. And that'll be 70. Then, of course, you check, pick the right alternative hypothesis. And this is a left-tailed test, so I need the middle one. Okay, so a lot of you will have calculators that don't have the bit about the color. Don't care about that. Calculate. Well, there's our test statistic, negative 2.58, which is what we got. And there's the p-value, 0.0049, which we got. All right, so that's terrific. Oh, there it is. On the graphing calculator screen on the right. All right, so there it is. So come down here. Here's another one. Yeah, once you get the hang of these, it's not going to be too bad. Per capita credit card charges for residents in New Hampshire and New York. So once again, we're going to follow the guideline that whatever data you see first will be group 1. And then whatever you see in group 2 will be group 2. So New Hampshire will be first. New York will be second. And we'll go from there. So these are the two mean charges are saying 3,900, 3,500. So let's selecting 50 from each state. So, okay, this time both the sample sizes happen to be the same, but as we saw from the last problem, that's not critical. And then here are the standard deviations, 900 for New Hampshire, which is group 1, 500 for New York at group 2. The two samples are independent at alpha equals 0.01. Is there enough evidence to conclude that there is a difference in mean credit card charges? Okay, difference implies not equal. Doesn't mean one's necessarily bigger than the other, just means they're different from each other. So here's the null and the alternative, equal and not equal. Claim being not equal. So we're trying to decide, are we going to reject that null in favor of that alternative not equal? So like I said, New Hampshire's group 1, so I have its data written over here. New York's group 2, so I have its data. Now this time I just did it this way. If you try to do it one step in the calculator, be very careful. You might not want to do it that way, and I can't blame you. But you know, the last example, I did this standard deviation, the square root part, you know, off to the side, right, first, and then put it back in there. Let me show you. Where'd it go? Yeah, see, I did this calculation by itself, then put it in there. But this time I'm putting all of it in there at once. And you can see I did it in the calculator with very careful use of parentheses. All right, so put that in the Z formula, and you're going to get 2.747. So if we use p-values, this is a two-tailed test. So p-value means if you're doing this manually, whatever you get positive or negative, you might as well put the number on both sides. Really, to get the p-value, all you have to do is you can get the negative off of the chart and just double it because it's symmetrical. Whatever you find on the left is the same as the right. So you see, as I have written right here, it's the same as just saying 2 times the area left of negative 2.75. And then you look up negative 2.75 on the chart, you're going to get 0.030 on the Z chart. 2 times that will give you 0.060. 0.060, that is less than negative 1. I'll find that 2.75 real quick. There it is. All right. Yeah, because it's got that extra 0 in front of it, so it makes it smaller. So where the p-value then is less than alpha, which means we reject the null, and there is sufficient evidence to support that the means are not equal. And then here's the rejection region thing, and I copied this, so in the notes here I have the same thing I showed you for the last problem. Now, this is a two-tailed test. Two-tailed always has a plus or minus associated with it. So it's two-tailed alpha 0.01. You can find right here, two-tailed alpha 0.01 is plus or minus 2.575. So our decision statement then would be, decision rule would be that we reject the null if Z is less than negative 2.575 or if Z is greater than positive 2.575. So I drew a little picture. Our calculated test statistic from above was 2.75, so yes, that does fall in our rejection region, and therefore we reject. So as we expected, it yielded the same answer. So here's the calculator input. I won't go back through that again since we just did one. But I would have chosen, you see right here, I would have chosen the not equal as the alternative hypothesis for this one. It's very important for the p-value. You would not get that right if you didn't make it. It would still produce the same test statistic. It wouldn't affect that, but it would affect the p-value. So it's already taking care of the doubling internally there. So the 0.060 is the answer. You know, here we had to multiply it by 2, but it's already doubled down there. So okay, a guidance counselor claims that the high school students in a college prep program have higher ACT scores than those in a general program. So we're going to treat the college prep program as group 1, general program group 2. So we have the data here for the college prep. 49 students selected. The mean was 22.2. Standard deviation was 4.8. And the group 2, which is the general program, has 44 students. 20.0 and 5.4 for their standard deviation. At alpha equals 1.10, can you support the guidance counselor's claim? So the claim is the college prep is higher than the general program. Higher meaning larger. So that's how we have mu1 greater than mu2. So therefore its alternative would be mu1 less than or equal to mu2. So I just wrote the data over here in a sort of a little organized format. So there's the formula again. So it'll be 22.2 minus 20 in the numerator, x1 bar minus x2 bar. The denominator would be the first standard deviation, 4.8 squared, divided by the first n, which is 49, plus the second standard deviation, 5.4 squared, divided by the second n, which is 44. All that part's under a square root, and then the whole thing, the numerator divided by the denominator, should be 2.07. Which you can see in this calculator box right there at the top, 2.07. Then I also did the normal CDF method too, which is fine. All right, so p-value method. Well, we need the p-value first, and we're comparing it. The 0.10, I just put 4 zeros there. That's the same 0.0 from up here, but I just add a couple extra zeros to show it a little bit easier. Now the 0.192, you see I did a normal CDF there, but we've learned in the past that when you have greater than, whether it's positive or negative, you can change it to less than and use the opposite sign. So to the right of positive 2.07 is the same as left of negative 2.07, which would be right there at 0.192. Okay, so 0.192, that's your p-value. So 0.192 is less than 0.100. Therefore, we are rejecting. And we support the claim that the college prep scores, ACT scores, are higher than the general program ACT scores. Then you can do the, so there's the critical value would be 1.28 from right up here in that chart. Yeah, right-tailed 0.10 is positive 1.28. And so still reject. It looks like we've had reject every time. Don't assume the answer is reject every time, but we've had quite a few rejects here. So what's this money spent eating out? Well, I'm not going to read through this problem. Let's come down here. Let's come to the punchline. So restaurants think that they're trying to check to see if they think age of 25 group spends less than households headed by people aged 65 to 74. So the group 1 will be the under 25 folks, and then the group 2 will be the 65 to 74 folks. And then therefore we're saying, claiming that mu1 is less than mu2, that group spends less. So that'll be your alternative. Then the opposite of that, which is the null, is greater than or equal to. So over here to the right, I wrote all the data for the under 25. Let's see how we did. 1876 is their mean amount spent. 113 is standard deviation, and there was 30 in that group. Group 2, also 30. They spend 1878. Standard deviation is 85. And alpha equals 0.05. Can you support the Restaurant Association's claim? So you calculate the test statistic. Like we've done before, you get negative 0.077. So nothing particularly strange there. So, which I rounded to negative 0.08. That's where that's coming from for chart purposes. So be careful that you don't confuse negative 0.08 with negative 0.80. So that's not it. It's got to be let's see. All right. Right here, I really should have a negative in front of this 0, 0. Yeah, there's 4681. That's your negative 0.8 value. Well, it wouldn't matter too much because that's 0.4681. That's way greater than 0.05. So we fail to reject. Therefore, we do not have enough evidence to claim that the 25 to 34 group, or under age 25, we don't have enough evidence to conclude that they spend less. We just can't say it based on that data. Now the rejection region, left tail 0.05 is negative 1.645. From right there, okay, so our test statistic is nowhere near the rejection region. See right there, so failed to reject. And that concludes our video.